Okay, we saw in our previous slide that one way to think about the wireless channel is as a source of additional distortion for our signal that must be somehow reduced or mitigated. And the whole purpose of diversity techniques is to do exactly that. Basically, diversity techniques ensure that the information signal travels through multiple paths to the receiver. If the fading on these paths is different, then we can somehow combine these multiple copies in order to improve performance. And the basic idea is that if one of the copies is experiencing a deep fade, as long as the fading is different on the other copies, we can choose one of the other copies that is not in a fade. So that would be a very simple form of selection combining. But as we'll see, there are other combining techniques as well. Now, there are several types of diversity, or basically several ways to get multiple copies of the signal to the receiver through multiple different fading paths. The first technique is time diversity, where you basically take an information symbol and disperse it over multiple coherence intervals that each experience different fades. And so when you receive all these symbols, you can combine them and reduce the effects of fading. The second type of diversity is what's known as frequency diversity. And here basically we consider a frequency selective channel, which in the frequency domain means that different frequencies experience different fades. And we basically take the information symbol and spread it out across frequencies so that when some copies of the information symbol are at frequencies that are experiencing a fade, other copies will hopefully be at frequencies that are not. The final type of diversity is what's known as space diversity, and this is implemented using multiple antennas. So we have, for example, a system with multiple antennas at the receiver. As long as those antennas are spatially separated by some distance, the fading experienced by each antenna will be different. We then route those received signals back to a common point, and we can combine them and reduce the effects of fading that way. So what we're going to do is we are going to talk about all three types of diversity, time, frequency, and space. And the first type of diversity we'll talk about is time diversity. And so, as we said in the previous slide, time diversity systems take an information symbol and spread it out over multiple time intervals or multiple coherence intervals. And the idea is that we spread it out over such a wide interval that the channel changes sufficiently that the different symbols experience different fading values. Usually the way we spread things out in time is using a code. So an error correction code, or any type of code, takes an information symbol or a group of information symbols and maps that information to a code word. And the code word is always longer than the original information symbols. It always contains more bits or more symbols, if you like, because codes always add redundancy to the signal. And so what we're going to assume is the simplest form of coding, which is a repetition code. And so the idea is we take an information symbol and we just repeat it a bunch of times. And if we repeat it over a long enough time interval, some of the copies will experience different fades than others. The problem with this, however, is that fading is a very gradual process, and we saw this in the wireless channel module. So if we look at the profile of fading as a function of time, it's not an instantaneous change, it's a very gradual change. And most symbol intervals are extremely short relative to the channel coherence time. So symbol intervals are on the order of microseconds or even tens of nanoseconds, and most coherence times are on the order of several milliseconds. So we would have to repeat a transmitted symbol thousands and thousands of times in order to span multiple coherence intervals. And that's just too much redundancy. That slows our system down too much. So with any sort of practical length repetition code, we're faced with the problem that basically the coherence intervals are so long that all of our repeated symbols are essentially going to experience the same fading value. We can get around this problem using something called interleaving and deinterleaving, which is sort of a special kind of a clever technique to take adjacent symbols in a repetition code and spread them out over very long intervals such that they do, effectively experience different fading values. So what I'm going to do is illustrate how an interleaver and a deinterleaver works, assuming a 9-bit frame processed by a simple matrix interleaver-deinterleaver structure. Now, what I should mention here is that most interleaving is conducted over frames that are much, much longer than 9 bits, usually hundreds of bits, thousands of bits. So this is just a simple example to give you an idea of how interleavers and deinterleavers work, and then I'll talk about why it's necessary to use much longer frames. So this example, or this top part of the slide, starts out by showing the interleaver structure. So here we have our 9-bit frame, and in this case each of these numbers don't represent the value of the bits, it represents the bit position, right? So the first bit is number 1, the second bit is number 2, and so on. The interleaver structure is essentially a matrix structure, and this is one of the simpler forms of interleavers. There are other forms. But basically, it's a 3x3 matrix, and we read our information frame in row by row. So the first frame, we read the first 3 bits into the first row, the next group of 3 into the next row, and the final group of 3 into the third row. Now, when outputting the information, or when outputting the bits from the interleaver, we output them column by column. So the first 3 bits in the output frame correspond to the first column. The second group of 3 correspond to the second column, and so on. And so the net effect of this reading in by rows, reading out by columns, is that we essentially get a shuffled or a scrambled form of the frame at the output. And fundamentally, that's all interleavers do. Interleavers are scramblers or shufflers. They just shuffle the order of the bits. Now, let's assume that our scrambled frame is transmitted over a fading channel, and what I'm showing with this curve here is basically the received power of the channel. And what happens is the first 3 bits experience relatively good channel conditions. The middle 3 bits, however, are subject to a fade. And so I'm kind of assuming that this is the interval over which a fade occurs, and then miraculously the channel recovers, and then the final group of 3 bits experience good channel conditions again. And so thanks to this fade, the middle 3 bits are going to be very weak, very prone to error. And I indicate the 3 bits that experienced poor channel conditions in red. And so the white bits experienced good channel conditions, the red bits experienced poor channel conditions. Now we move on to the deinterleaver. So the interleaver is a structure that lives in the transmitter. It scrambles the bits in the transmitter. We then send the scrambled frame through the channel, and then in the receiver, we have a de-interleaver that exists basically to put the bits back into the correct order. And so it usually has a structure similar to the interleaver, but it always performs the inverse of the interleaver operation. So here we have our scrambled bits, with our 3 red bits that experience the poor channel conditions, where the interleaver read in the bits row by row. This interleaver, the de-interleaver, reads them in column by column. So the first 3 bits are read into the far column. The second group of 3 bits are read into the middle column, and so on. Since we read in column by column, and the de-interleaver performs the inverse of the interleaver, we output row by row. And so the first group of 3 bits corresponds to the first row of the de-interleaver. The second group of 3 bits corresponds to the second row of the de-interleaver, and the third group of 3 corresponds to the third row. Now, 2 very, very important things have occurred here after the de-interleaver operation is complete. First of all, you'll notice that the bits are back into their correct order again. So the first bit is bit number 1, the second bit is bit number 2, and so on. The second important thing that's happened is that the bits that experienced sort of similar or common channel conditions have been scattered throughout the frame. And so the middle group of 3 bits that experienced poor channel conditions are now scattered throughout the frame. So we have bit 2, then we have 2 good bits, then we have bit 5, then we have another couple good bits, and then we have bit 8. And so basically what the de-interleaver does is, as it descrambles the received frame, it essentially scrambles the fading profile of the channel. And so we, in the end up with adjacent bits that experience very, very different fading conditions. Now, one more important comment here is regarding the length of the frames. So an interleaver and a de-interleaver operate on a frame-by-frame basis. And so it's important that the frames are long enough that they are long enough to encompass several coherence times of the channel, right? So an interleaver and a de-interleaver only shuffles within a frame boundary. And so if the frames are really short, and the whole frame experiences kind of a common fade because it's shorter than the coherence time of the channel, then shuffling that frame doesn't really matter. You're basically shuffling bits that all experience the same fading value. So long frames are very important. However, you can't have the frames too long, because the disadvantage of the interleaver and de-interleaver structures is that it introduces delay into our communication system. So the interleaver structure cannot start outputting its first bit until the matrix is fully loaded. And so there's basically a delay equal to 1 frame time to load the interleaver, and a delay equal to 1 frame time to load the de-interleaver, and that can cause a bit of latency in the communication link. One other final comment is that this matrix structure is a very, very simple interleaver structure. There are many interleaver structures out there, pseudo-random interleaver structures, and you'll see a variety of them if you end up working with time diversity or error correction for wireless systems. So as I mentioned in the previous slide, to be effective, interleaver frames must be longer than the channel coherence time, and the penalty of using an interleaver-deinterleaver structure is delay. What we can do now is present a little bit of a mathematical model or an equation for that's useful for characterizing a diversity system. So we can think of the multiple received copies of the transmitted signal as a vector, y. And so y carries the L copies of the transmitted information symbol. In this case, the copies of the L times repetition code, right? So we repeated our information symbol L times. And so this vector of received signal samples is equal to the transmitted information symbol. So there's only one transmitted information symbol, and it was repeated L times, multiplied by a vector h, and h contains all of the different fading values corrupting all of the different copies of the transmitted signal. Now, ideally, all of these fading values are different. Let's say we used an interleaver structure that very effectively spread our information over a very wide range of times, and maybe we can even go so far as to assume that the fading corrupting these diversity samples is independent. However, we won't always have that case. Actually, typically, we won't have that case. Finally, W is a vector of noise samples, and because each of the different copies of the transmitted signal were received at different times, those samples would be corrupted by independent additive white Gaussian noise samples. And the noise definitely always is independent. So the fading value is not necessarily independent, but the noise definitely always is. And so basically now we can take these multiple copies of the transmitted signal and combine them somehow. And we'll get into how that combining is done and how it improves system performance a little bit later on. What I'm going to do first, though, is move on to talk about frequency diversity and then space diversity, because as we'll see, even though these techniques are implemented very differently, they basically give us almost exactly the same result, almost exactly the same type of received signal. So, moving on to frequency diversity. Frequency diversity is present anytime you have a frequency selective channel. And the benefit of frequency diversity can be harvested in the time domain. So if you remember, if you have a frequency selective channel in the time domain, you end up with a channel impulse response with multiple taps. Now, this can have some negative effects. For example, the multiple taps will sort of spread or smear your transmitted signal, and you need to deal with that, perhaps with some sort of equalizer structure. But it turns out that if you do maximum likelihood detection in order to mitigate or deal with the intersymbol interference caused by this symbol smearing, you actually get a diversity benefit as well. It seems a little bit counterintuitive that this distortion would actually help you, but essentially what's happening is that you are receiving multiple copies of the transmitted signal, right? So you receive one copy of the signal in the desired symbol interval, and then you get multiple copies in subsequent intervals sort of interfering with the next symbols. Maximum likelihood detection is able to do two things for us. Not only does it sort of deal with the interference or the intersymbol interference, it can also take advantage of the redundancy in the signal caused by that smearing and improve overall performance. The problem, of course, with maximum likelihood detection is that it's quite complicated. It's fairly complex, and that was the whole reason why we went and looked at those suboptimal interleaver structures. A lower complexity time domain method for harvesting the benefits of frequency diversity is a structure known as the rake receiver. And the rake receiver is used with spread spectrum communications, where your transmitted information symbol is multiplied by a code, a spreading code. And at a very high level, what the rake receiver does is separates out the different delayed copies of the received signal due to the channel dispersion. So essentially, the frequency selected channel has multiple channel taps. That means you receive multiple shifted versions of the transmitted signal at the receiver. Normally, these multiple shifts just add together and cause sort of a smeared pulse shape. However, the spreading codes actually allow the rake receiver to separately extract each one of these shifted versions of the received signal, and once you do that, you can perform diversity combining on those all those shifted copies of the signal. And this is all thanks to the property of that spreading code that's multiplied over top of the information symbol. And so the rake receiver was very popular, or is very popular, particularly in CDMA or code division multiple access communication systems. And it is much lower complexity than maximum likelihood detection. However, OFDM, or orthogonal frequency division multiplexing, is now by far the most popular choice for implementing frequency diversity in wireless systems. So spread spectrum and CDMA is still very common. Many cellular systems still use it. However, most of the next generation systems and the high throughput sort of wireless LAN systems are now migrating almost exclusively to OFDM. And so I'm going to talk about frequency diversity in the context of OFDM, because I feel that's the most relevant for a research class. So we know that OFDM transmits information on multiple orthogonal carriers spread across the frequency domain. We also know that a frequency selective channel basically has a bunch of fades in the frequency domain that look exactly like sort of the gradual fades that you see when you look at a fading profile in the time domain. And so basically exactly like we did in the time domain, OFDM signals achieve frequency diversity by creating multiple copies of the transmitted symbol and spreading them out across carriers that are spaced wide enough apart that they experience different fades. And so it's a very, very similar picture to what we had in the time domain. Now, it turns out that we're faced with also a very similar problem to what we had in the time domain. So the coherence bandwidth of an outdoor channel is usually a bit under 500 kilohertz, but it's relatively wide. And so what that means is basically all of the frequencies that are within a 500 kilohertz bandwidth experience approximately the same fading value. The problem is that subcarrier spacing is much, much lower than that. And so that means that the fading experienced by adjacent carriers in the frequency domain is going to be very similar. This is exactly like the time domain scenario where we used our repetition code, but we realized that because of the long coherence time and the very short symbol intervals, we could repeat the symbol many, many times, hundreds of times, and all of those copies of the symbol would experience exactly the same types of fading. So the solution in the frequency domain is exactly the same as it was in the time domain. We would use an interleaver-deinterleaver structure to sort of scramble the information symbols before we put them on the OFDM carriers. Assuming that we use a repetition code that spreads the symbol over L carriers, exactly like we used a repetition code to spread the symbol over L symbols in the time domain, the received symbol equation for frequency diversity is identical to what we had in the time domain. So we have a vector containing L received signal samples, and that vector is equal to the transmitted information symbol x that got repeated L times, multiplied by a vector of L fading values, maybe they're independent, maybe not, plus a vector of additive white Gaussian noise, and the symbol samples and the noise samples in this vector are independent, just like they are with conventional OFDM. So the big picture here is that when we consider frequency diversity from an OFDM perspective, it looks almost exactly the same as time diversity did, and we get basically the identical received signal equation. Okay, the final type of diversity that I'll talk about before we get into our discussion of combining and performance analysis is spatial diversity. And you'll notice here that I'm using a particular kind of spatial diversity, which is receive antenna diversity. So as I said in the introduction to the diversity module, spatial diversity is achieved by using multiple antennas. And the idea is that if you have multiple antennas that are spaced by a certain distance, because they are a different position in the environment, they will experience different fading. And so you can either transmit with multiple antennas or receive with multiple antennas, and you should get different copies of the same symbol traveling over different fading paths. However, as we're going to see, it's much, much easier to implement spatial diversity with multiple antennas at the receiver than it is multiple antennas at the transmitter. It is possible at the transmitter, and I'll talk about how that's done. It's essentially an introduction or a look into the area of space-time codes. However, it's most easy to introduce the concept using receive antenna diversity first. So, as I said, we can implement either multiple antennas at the transmitter, which is what's known as transmit diversity, or multiple antennas at the receiver, which is known as receive diversity. Or we can have both, and we'll see that when we look at our analysis of MIMO systems. So if we consider the received signal from L spatially separated receive antennas, again we get exactly the same equation that we had for the time diversity case and the frequency diversity case. And so let's take a look at it. What we assume here is we have L spatially separated receive antennas. These antennas would be separated by a certain distance. They would each have their own sort of dedicated receiver path, receiver hardware connected to them. And so at the output of those receivers, we have L copies of the transmitted symbol. So we're assuming here that the transmitter uses just one antenna. That symbol is received by L receive antennas. And so naturally we get L copies. And so the output of all of these L receiver chains connected to the L antennas is contained in Y. That's equal to the transmitted symbol X multiplied by a vector of fading values. Each fading value represents a different spatial path to a different receive antenna. And the additive noise corrupting each of the samples again is independent because it's arriving from the thermal noise in each of these individual spatially separate, or each of these individual dedicated receiver chains connected to the spatially separated antennas. So one of the main things that I wanted you to take away from our initial discussion of time, frequency, and space diversity, or receive antenna diversity, is that the received symbol equation is exactly the same for all three cases. And so what I can do now is do a diversity analysis for this equation, and it applies equally to all three forms of diversity. So it's a very generic derivation in that sense. So we have these L copies of the transmitted symbol, all experiencing different fading values, ideally. And the question is, how do we combine them? What do we do with them? One simple form of diversity combining, and this is what's known as selection diversity, is to just look at all of the samples and select the one with the maximum amount of energy. So in every symbol interval, just pick the biggest one. And that's not a bad strategy, and it certainly does improve system performance, but it's not optimal in the sense of maximizing the signal to noise ratio at the output of our receiver. Now, whenever we talk about maximizing signal to noise ratio, we always go back to the matched filter derivation. And essentially, if you remember when we were deriving the probability of error for BPSK over a Rayleigh faded channel, when we wanted to figure out the optimal receiver for that wireless signal, we basically modified the matched filter. We said, okay, the channel distortion is essentially changing the pulse shape of our transmitted signal, and so the matched filter should match to that distorted pulse shape, and if it does, we get a maximization of signal to noise ratio and essentially an optimal receiver just from that perspective. And so what we're going to do here is basically exactly the same thing except for a vector signal now. So we're assuming that Y represents L complex samples of a waveform that represents our transmitted signal X, right? And so this is an analog waveform that represents a single transmitted signal. And so we know that the way to maximize signal to noise ratio when we have a bunch of samples of a waveform is to run it through a matched filter. And so if we create a matched filter that is matched to the channel distortion H, basically what we do is we take our received symbol vector Y and we multiply it by the conjugate transpose of H. This is essentially just a matched filter structure for our received signal. The other thing we do here is we normalize the conjugate transpose of H by the norm of H. This normalization factor is basically to ensure the variance of the noise remains unchanged, and it serves much the same effect as the normalization did in our BPSK derivation. And so, if we take the equation for Y and we substitute it into the equation down here, what we end up getting is our transmitted symbol X multiplied by the norm of H. And remember, the norm of a vector is a scalar value, right? So we're dealing with a scalar value here, plus the noise multiplied by the conjugate transpose of the channel vector. And this is also a scalar vector, or sorry, this is also a scalar value because W, which is a column vector, multiplied by the transpose of H, which is a row vector, gives us a scalar. This, so we've taken this this perspective of looking at this from a matched filter point of view, but essentially taking a vector of received diversity signal copies, multiplying it by the conjugate transpose of the channel is a technique that's known as maximal ratio combining. And as we were saying from a matched filter perspective, it's been shown that for constant variance additive white Gaussian noise, maximal ratio combining is optimal in the sense that it maximizes the signal to noise ratio at the output of our receiver. Now, when we should talk just a second about this scalar noise term. So essentially, when we take W and multiply it by the conjugate transpose of H, what we're doing is we're adding up a bunch of noise samples, right? So each noise value is scaled by a channel value, and all of these terms are added up, then multiplied by 1 over the norm of the H vector. So if you take a bunch of Gaussian samples and you add them all together, your distribution is still Gaussian. Normally, this scaling by these channel vectors or these channel values would change the variance of the noise. However, thanks to this normalization term out front here, the variance doesn't change. And so essentially, the noise is left unchanged. It's still Gaussian noise, and it has exactly the same variance as the individual noise terms making up the vector W. So the nice thing about this is that we can jump straight to using the conditional probability of error for BPSK that we derived for the Rayleigh faded channel. So if you remember, with the Rayleigh flat faded channel, we had our noise variance was unchanged. So we had n naught in our term, or in our square root term. We had our original energy per bit, which was sort of our original BPSK symbol energy. And then in our old BPS or Rayleigh faded derivation, the term out front was the magnitude squared of the single flat Rayleigh faded channel term. However, here, if we just jump back, we can see in this equation our desired signal or our desired symbol is not multiplied by the magnitude of a single Rayleigh faded term, it's multiplied by the norm of a vector of channel terms. So it's still a scalar value, but it's the norm of a vector of terms rather than the magnitude of a single term. But otherwise, it's exactly the same. So here we have EB over N naught scaled by a scalar term that is a function of the fading channel, except now it's a function of the vector of channel values rather than a single Rayleigh faded channel value. Now, if we assume Rayleigh fading, then the squared norm of our diversity channel vector is equal to the sum of the magnitude squared of the individual channel terms. And if we're assuming Rayleigh fading, these individual channel terms are zero mean Gaussian random variables. And when you take the magnitude squared and you add them up, you get a chi-squared distribution with 2L degrees of freedom. This is a typo up here. This shouldn't be 2L. That should just be L. But because we have a real and an imaginary term for each of these channel values, we get a chi-squared distribution with 2L degrees of freedom. So before, our distribution here for our single flat Rayleigh faded channel derivation, this was exponentially distributed. Now, the channel fading term here is chi-squared distributed with 2L degrees of freedom. So basically, as we increase L, as we add more diversity paths, the distribution of our channel term is going to change, and this is going to have a very, very important effect on the performance of our system. Another sort of interesting perspective that we can take is that we can essentially assume that this chi-squared distribution represents the effective fading experienced after diversity combining. And that's kind of an interesting perspective. So before the channel term, or the term that we had in front of EB in our bit error rate was the magnitude squared of a Rayleigh distribution, which was exponentially distributed, and that was fine. But that was caused by the channel. I mean, that was a property of the channel. There was really nothing we could do about controlling it. Here now, though, the term in front of EB is a distribution that is actually under our control. So this parameter L is the number of diversity paths that we have, and we can change that. That's a design parameter in our system. And as we change L, we will see that this effective channel term that we have in front of EB, this channel term that basically we create thanks to our diversity combining, is going to change. And so it's useful to take a look at what those distributions look like. So what we're showing on this slide is a chi-squared distribution where L is equal to 1. So we have a diversity system with just a single path. Now, normally if we only have one diversity path, we wouldn't call this a diversity system at all. And in fact, a diversity system with L path, with one path, is equivalent to the original BPSK bit error rate derivation that we did at the start of this module. So there's no diversity, it's a single flat Rayleigh fading path. And we saw in our original derivation that when you take the magnitude squared of a Rayleigh distribution, you get an exponential. And we see that's exactly what we have here. So if there's only one diversity path, we have an exponential distribution, and we've already plotted the bit error rate for that earlier on in the course module. Now let's see what happens when we add two diversity paths. So here we're showing the original distribution for 1, the exponential distribution, and now we're showing the fading distribution for 2 diversity paths. It's a very important thing to compare the shapes of these two distributions and understand how they affect the performance of a wireless system. So essentially, we can think of these distributions as representing basically the fading, the effective fading of the channel after diversity combining. So if we have no diversity, we can see that the distribution, the exponential distribution, has a relatively large value in this range over sort of that range on the x-axis. Basically, what that tells us is that this distribution spends a lot of time, or the channel spends a lot of time close to 0. So if the PDF has a large value in this sort of low range on the x-axis, then the signal is spending a lot of time here, and it's spending a lot of time in fading, in deep fades. When we added just one diversity path, we can see that the shape of our distribution has changed quite dramatically. So effectively what we've done is we've taken that original distribution and we've started to pull it away from 0. So now we have a shape where, yes, we still do have, significant distribution, a significant portion of our distribution is in this, heavy faded range close to 0. However, it's much less than we used to have with the exponential distribution. And now we've got a range here where the distribution is starting to move away from 0, and it's starting to concentrate more and more about the mean, which is in this case normalized to be 1. And so that's the effect of diversity. As we add more and more diversity paths, what happens is our fading distribution spends less time close to 0 and more time concentrated around the mean of 1. So it effectively reduces or eliminates the amount of variation we see in the signal due to fading. And so we can continue this by adding the distribution for 4 diversity paths. We can see when we look at the curve for 4 diversity paths that the trend is continuing. We're becoming more and more concentrated around the mean, and we're pulling away from those very low values close to 0. And so we're getting a nice sort of nice strong narrow concentration around the mean. And if we add 6 diversity paths, again, we see the trend continue. And it's particularly dramatic if you look at the curve for 6 diversity paths and you compare it with the curve for 1 diversity path. You can see that we've really moved away from 0 and we're much more concentrated around the mean. That means we see less variation in our signal and we spend a lot less time in these very, very deep fades. Another second point, equally important, is the relative change that we see between these distributions. And so I'll back to the case where we have 1 diversity path and then we add a second one. So by adding just 1 more antenna, we see a very dramatic change. So the distribution for L is equal to 2 is really a lot different than the exponential distribution. Now, let's go from 2 antennas to 4 antennas. You know, there was a change here, so the distribution definitely did change, but we had to add 2 additional paths rather than just 1 additional path to get a change that wasn't quite as dramatic. So the change from L equals 1 to L equals 2 was quite dramatic. The change from 2 to 4, also dramatic, but not quite as much. Why is this important? It's important because diversity has a cost. For example, if we're talking about antenna diversity, to go from 1 to 2, we had to add a second physical antenna and a second dedicated receiver for that antenna. That hardware costs money. When we go from 2 to 4, we had to add 2 antennas and 2 dedicated receivers for not quite as dramatic an improvement. If we go from L equal to 4 to L equal to 6, again we see a change, but it's not quite as dramatic as even the change from 2 to 4. But still we had to add 2 more dedicated antennas. And so what I'm trying to illustrate here is that diversity adds on the basis of diminishing returns. And so if you have no source of diversity and you add a single additional diversity path, you see a big improvement. However, if you go from 2 paths to 3 paths, even though you're spending the same amount of incremental money, you're not going to see the same sort of dramatic improvement in performance. So, and this again is important because there's a cost to diversity. When we're talking about spatial diversity, it's sort of a hardware cost. When we talk about time and frequency diversity, it's a cost in throughput. So if we want more diversity paths, we have to repeat our symbol more times. In the time domain, that means we have more redundancy and we basically have to slow our system down because we're repeating our information symbols so many times. In the frequency domain, these extra repetitions use up our carriers, and so we have more carriers dedicated to transmitting essentially the same information, and that lowers the overall throughput of our system. And so diversity, while it does have a benefit, it definitely has a cost, and as you add more and more paths, that sort of incremental gain that you get will start to go down. And that's a very important thing to remember about diversity. So when looking at the gain or the benefit provided by diversity, we find that we get essentially 2 forms of gain. The first is what's known as diversity gain, which is a reduction in bit error rate due to altering the channel fading statistics. And that's basically what I was trying to illustrate on the last sequence of slides, where we showed how adding more diversity paths changes the PDF of the distribution. And it's important to note that, in those slides I kept the distributions normalized so they all had the same mean. So there wasn't necessarily a gain in average received power. It was basically just a bit error rate gain due to the changing the shape of the distribution, spending less time close to 0 and more time concentrated about the mean. The second form of gain, however, from diversity systems is what's known as a power gain. And this is a reduction in bit error rate due simply to harvesting more received power due to the multiple received copies of the transmitted signal. Now, if we look at our signal to noise ratio, EB over N naught, multiplied by the squared norm of the channel vector, if we take the average value of this, we find that we get the average signal to noise ratio multiplied by L, right? So we've normalized all of our individual terms in that channel vector to be equal to 1. And when we take the squared norm, we essentially add up all those variances and we get L. So we get L times the received signal power due to the L copies over the different diversity paths. And that makes sense, right? L copies of the received signal, we would expect to get more transmit power. However, it's important to note that not all diversity systems enjoy a power gain. For example, received antenna systems always do enjoy a power gain, basically because we're putting more antennas into the environment. That means we can harvest more of the received power of the signal and we get an improvement in gain. However, in time and frequency diversity systems, we typically do not enjoy a power gain. And the reason for that is because when a repetition code is used, or any type of code, the transmitter generally keeps the amount of energy invested per bit constant. So, for example, if we are transmitting a single information bit using a 3 times repetition code, the energy in each of those repeated copies will be 1/3 of the energy invested in the original information bit. And the same goes for frequency diversity as well. So the transmitter generally does not invest more power when using a repetition code, or indeed any other kind of code. So we see power gain for receive antenna diversity, but basically not for any other form of diversity. So now the final thing left to us in our diversity performance analysis is just to derive the bit error rate of a diversity system. And to do that, we're going to follow a very similar approach to what we use to derive the probability of error for the non-diversity BPSK transmission over a Rayleigh faded channel. So to simplify our notation, just like we did in the other derivation, let's let the random variable V equal the squared norm of the channel vector. Again, this is the squared norm of the channel vector is a scalar value, so we can use a scalar random variable. And then, just like in the previous derivation, we integrate the conditional probability of error over the PDF of V. And so the integral setup is exactly the same. We take the conditional probability of error, multiply it by the chi-squared PDF of V in this case, and then working through a bunch of mathematics and making a bunch of simplifications, we end up with a fairly complicated expression where as a function of this variable mu, and the mu is actually is a function of the signal to noise ratio. And I give two versions of mu here. The first one is a function of EB over N naught, and this is for an antenna diversity system. And the second one is basically almost exactly the same, except EB over N naught is divided by L, and this term is used when you're dealing with a time or frequency diversity system where the total amount of energy invested in transmitting the symbol is divided when you make your repeated copies, either in time or in frequency. So this allows us now to take a look at the bit error rate curves of a diversity system. So here we have the probability of error versus EB over N naught for L equals 1, 2, 4, and 6 diversity paths. This is a time or a frequency diversity system, not an antenna diversity system. So the bit error rate here is changing just because of the change in shape of the fading PDF and not due to any power gain. So there's a couple of interesting things that we can point out. First of all, we see that the linear shape of the bit error rate curve in the fading channel is preserved. So we have a linear bit error rate curve for no diversity, just like we had before. And then an approximately linear curve for 2 paths, and an approximately linear curve for 4 paths. However, what we see is that adding more diversity paths essentially changes the slope of the bit error rate curve. We also see further confirmation that diversity adds on the basis of diminishing returns. So if we look at the incremental gain achieved when we go from 2 diversity paths to 4 diversity paths, we see a very large improvement, a significant improvement. And when we go from 4 diversity paths to 6 diversity paths, but we've added exactly the same incremental number of additional paths. However, we can see that the incremental performance improvement we've achieved is less than when we went from 2 to 4. And that's again because diversity sources add on the basis of diminishing returns. And just a last point in the diversity analysis section. This is an often used approximation for the bit error rate of a diversity system at high values of signal to noise ratio, where that bit error rate curve basically turns linear. And when we make this approximation, we can now clearly see how diversity order affects the slope of the bit error rate curve. So here we have an inverse function to signal to noise ratio, and this exponent L is basically what changes the slope of that straight line bit error rate curve when shown on the log plot of the previous slide. And so this equation basically confirms the observation that increasing diversity order changes the slope of the bit error rate curve. And just a little bit of terminology, the slope of this line is often called the diversity order of the system. So if we have 2 diversity paths, we would say that the diversity order of the system is 2. 4 paths, we would say that the diversity order of the system is 4. Okay, so the final topic to discuss in the diversity section of this model is transmit antenna diversity. So we alluded earlier to how it's simpler to implement spatial diversity with receive antennas than it is with antennas at the transmitter. And so let's talk a little bit about why that would be. So is it possible to implement spatial diversity using multiple transmit antennas? It is, but unfortunately it ends up being a little bit harder. Now, why is that the case? Well, one thing that it's important to note about diversity paths is that in order for diversity to work, all of these paths have to remain independent, they have to remain separate, or in other words, they have to remain orthogonal to each other. So you can't have diversity paths that are forming linear combinations of each other, because then there starts to form dependency between the fading on those paths, and the whole benefit of diversity starts to fall apart. So the big challenge with using, let's say, 2 transmit antennas is to keep the two paths from the transmit antennas orthogonal once they reach the receiver. So if we consider the case with 2 transmit antennas and 1 receive antenna, if we take 2 copies of an information symbol and we transmit them at the same time from those 2 antennas, those signals will just add together in the radio channel, and they'll be impossible to separate at the receiver. We'll still be able to recover the information, but there won't be any diversity combining because the receiver just gets one copy of the signal that is the linear addition of the two paths. And just doing a straight linear addition of diversity paths does not give you any form of diversity gain. You have to use maximal ratio combining, selection combining, or something like that. Now, the trivial solution to solve this problem is to basically transmit in orthogonal time slots. So you divide the transmit time axes into slots. You take two copies of a single symbol. You transmit the first copy from antenna 1 in the first time slot, and then the second copy from antenna 2 in the second time slot. The receiver is able to decode both of these signals separately, can store them independently in a buffer, and then perform maximal ratio combining on them. And because the first signal arrived from one antenna and the second signal arrived from the other antenna, they experience different fadings or different fading values, and because they arrived in two different time slots, they're orthogonal to each other. And you could imagine doing this with different frequencies or even perhaps different orthogonal codes. The problem with this, though, is that this basically cuts our data rate in half. So if we consider the two antenna case, it cuts our data rate in half. And so we can achieve transmit antenna diversity, but at a penalty to our data rate. And if you'll remember, there was no penalty to data rate with receive antenna diversity at all. We just put up a second receive antenna and we just got our second copy. You know, not quite for free, but certainly from a throughput perspective, it didn't hurt our throughput at all. So the logical question is it possible to achieve transmit diversity without sacrificing data rate? As it turns out, the answer is yes for two antennas, but unfortunately no for more than two antennas. For the special case of two antennas, we achieve basically the equivalent to maximal ratio combining with no penalty in data rate using something called Alamoudi coding, which was a very famous diversity technique developed obviously by Alamoudi. And so I'm going to talk about Alamoudi coding for the two antenna case and show you how it works, and then I'll talk a little bit about how this is extended to more than two antennas. To illustrate how Alamoudi coding works, let's consider a 2x1 multiple input single output system, and the received symbol for the symbol at the receiver from the two transmit antennas is given by the following equation. And if we just take a look at it, the single received symbol sample coming out of our single receive antenna is the linear summation of our two signals from our two transmit antennas. So here we have the subscripts indicate antenna number, so this is the information symbol. So X1 is the information symbol transmitted by the first antenna. H1 is the fading between the first antenna and the receive antenna. The second term, X2, is multiplied, or the symbol from the second antenna is multiplied by the channel fading term between the second antenna and the receive antenna. And we just have one additive noise term corrupting the received symbol. And so this is what we have. And the challenge is to separate these received symbols somehow and perform diversity combining on these two fading paths. So Alamoudi coding does this by using a very special form of essentially what is now known as a space-time code. And so if you read Alamoudi's original paper, he really provides almost no explanation as to how he came up with this. He just sort of presents it, shows that it works. And so this is perhaps something that he was able to just sort of intuitively determine. and it's since then sort of been or sort of spawned the whole field of space-time coding. And so what we're going to do to simplify notation is we are going to consider two symbol intervals, so symbol interval 1 and symbol interval 2, transmit antenna 1 and transmit antenna 2. So Alamudi coding basically transmits two complex information symbols, U1 and U2. So U1 and U2 are the two information symbols that were being transmitted, and we're transmitting them over two symbol times. Okay, so two information symbols over two symbol times, no loss in data rate. During the first symbol interval, we transmit U1 from the first antenna and U2 from the second antenna. So nothing really unusual here. We just send one symbol from one antenna, the other symbol from the other antenna, and of course they're going to add together in the channel linearly and corrupt each other. So just using that first symbol sample isn't going to help us. However, in the second symbol interval, from the first antenna we transmit the negative conjugate of U2, and from the second antenna we transmit just the conjugate of U1. And it's not at all obvious at this stage how this allows us to perform transmit diversity, so we need to go a little bit further with these equations. The next key assumption for Alamudi coding to work is that the channel is fading slowly enough that the channel is basically constant between symbol intervals. So the channel fading term for antenna 1 at symbol 1, symbol interval 1, and at symbol interval 2 is just equal to H1. And we'll drop the symbol interval index to simplify our notation a bit. And we make the same assumption over here for the second antenna. Is this realistic? Well, we know that it is, right? Because channel coherence times are typically tens or hundreds of milliseconds. Symbol times are typically tens or hundreds of nanoseconds. And so this is a very good assumption for modern communication systems. And so what we're going to do is we are going to look at the received symbol at the single receive antenna for both of our symbol intervals. And so we look at the received sample for the first symbol interval, the received sample for the second symbol interval, and we set up our equation in sort of this matrix form where we have our channel vector, H1 and H2, multiplied by what is essentially a code matrix, but this contains our information symbols using the mapping that we showed above. And then we have an additive noise vector W as well. So in order to see how this works, we can manipulate the equation a little bit. We can change it around a little bit and write our received samples as a vector. Although remember, this isn't a spatial vector. This is a vector in time. These are samples received over two different time intervals. And we play a few games to put these equations in slightly a different form. First of all, we're writing the equation for the conjugate of y2 rather than y2 itself. And you can see over here we've formed a square channel matrix that is multiplied by a vector of our information symbols. And so basically it's these information symbols U1 and U2 that we want to recover from our received time samples Y1 and Y2. The way we achieve this is basically to use projections. And so in order to extract our first information symbol, U1, we take our received signal vector Y and we take its projection onto the first column of our channel matrix. And when we do this, and you'll notice to simplify things a little bit, I've dropped the noise terms, W. But if you pause the video and sort of look at these equations step by step, you'll see that the end results is equal to our information symbol multiplied by the magnitude squared of H1 plus the magnitude squared of H2, which is exactly the result that you get from maximal ratio combining. And so this first projection gives us the maximal ratio combining result for U1, and if we take the projection of the second, if we then project the received signal vector Y onto the second column of the channel matrix, then we get the maximal ratio combining result for U2. Again, with the noise terms removed, just to sort of simplify these equations a little bit. And so the reason why we're able to extract these information symbols is because the columns of this channel matrix in this special form that we've been able to manipulate are orthogonal. And so all we need to do is take the projection onto the first column vector, orthogonal column, to extract the first symbol, and then the projection onto the second orthogonal column to extract the second symbol. And it turns out that we get a maximal ratio combining weight in front of our symbols when we do this. And so we get maximal ratio combining from two transmit antennas with no penalty in data rate. Now, the question is it possible to do this for more than two antennas? The field of orthogonal space-time block codes has developed to try and answer this question, and it turns out that the answer is no. So you can develop similar space-time codes for more than two antennas. However, if you want the codes to give you perfectly orthogonal columns, like we have here, you're no longer able to transmit without a penalty in data rate. You do have to take a penalty for your data rate. As it turns out, there's also a technique called quasi-orthogonal space-time block coding, which gives you column vectors that are only partially orthogonal. So there's some interference between them. However, your data rate penalty is a lot less than with truly orthogonal space-time block codes. So there's many codes, and it's a very interesting area to examine all of the trade-offs that exist. But it was the original paper on Alamoudi coding that was the start, or the genesis for all of this subsequent interesting research.